Welcome to the AI Research Roundup. I'm Alex, and today we're looking at a paper from the Hugging Face trending list, published on July 8, 2025, just 2 days ago. This paper explores how to shrink the KV cache. That's the part of an LLM's memory that stores past context, by a factor of 4 to 7, without losing performance. The paper is titled, A Systematic Analysis of Hybrid Linear Attention, and its findings challenge some common assumptions about designing efficient models. To do this, the authors systematically trained and tested 72 different models. Alright, so to understand how they built these models, let's look at the different types of linear attention they tested. Linear attention is a more efficient way for a model to process long sequences of text. This figure shows 3 generations of these mechanisms. The first generation is the simplest, just updating a single list of numbers. The second and third generations use a more complex grid of numbers for memory, but the key difference is in the third. It uses what's called controlled forgetting, which lets it selectively erase old information before adding new data. This ability is crucial for preventing the model from overwriting important context. This table then details the specific math behind those 3 generations we just discussed. It shows the update rule, which is how the model's memory state gets updated with new text, and the readout, which is how it uses that memory to generate its output. You can see the different approaches, from simple vectors to more complex matrices. But the key innovation is in that third generation, the DeltaNet family. It uses what are called gates, basically learned switches that let the model selectively subtract or forget old information before adding new content. So how do they combine these different attention types? This diagram shows the hybrid architecture they tested. It starts with an embedding layer, which turns words into numbers, and ends with a projection head to generate the final output. The interesting part is in the middle, in the hidden layers. You can see they stack multiple efficient linear attention layers with just one layer of standard, full attention. This hybrid approach is the key. The linear layers keep the memory or the KV cache small, while the full attention layer helps maintain performance on complex reasoning tasks. Moving to the results, these charts show how that hybrid mix affects performance. On the left, we see language modeling performance, which is the model's general language skill. The lines are pretty flat, showing that the ratio of linear to full attention layers doesn't really change this general ability. But on the right, we have recall performance, the model's ability to remember specific facts. Here, the mix is critical. Performance drops sharply with fewer full attention layers. These results show that a sweet spot, maybe a 6-to-1 ratio, is needed to balance memory savings with strong recall. Building on that idea of a sweet spot, these charts visualize the trade-off, using what's called a performance efficiency Pareto front. This front just shows the best options that balance performance against efficiency, which is measured in flops or floating point operations. The goal is the top right corner. You can see the standard transformer, that red square, has top performance but is the least efficient. The hybrid models, like HGRN-2, offer a great compromise. And as the text gets longer in the right-hand plot, their efficiency advantage becomes even more dramatic. So, digging deeper into that performance side of the trade-off, this table shows the best performing model from each family on the Ruler benchmark, which is a suite of tests designed specifically for recall. We see results for different hybrid models compared to a standard transformer. The key takeaway is in that AVG column on the far right. Notice that the gated DeltaNet and the HGRN-2 models, which have those gating and hierarchical features we talked about, actually outperform the standard transformer on average. This is a huge deal, showing that these efficient hybrids can actually be better at remembering things. So, to wrap things up, this analysis shows that hybrid models aren't just about saving memory. With the right design, they can actually beat standard transformers, especially on recall tasks. The key is finding that sweet spot ratio, about 6-to-1, and using a linear component with smart features. Things like selective gating, which acts like a switch to control information flow, and hierarchical recurrence, which processes context at multiple scales. These allow the models to achieve top performance while being much more efficient. That's our show for today. Thanks for joining the AI Research Roundup. I'm your host, Alex.